Okay, now we're getting into the next unit, and what you're going to see on this unit that's coming up is much like a lot of the other units that we've been covering here in C-Scope lately. We learn a new skill, okay, learn how things work, learn how to use the calculator on them and stuff like that. And then they come along in the very next unit and they make us do the exact same stuff, but it's in more realistic, real life type situations, a lot of application stuff and things like that. Okay, so if you kind of got a good grasp of what was going on last unit, then this will be nothing more than applying it to some different situations like the worksheet that you've got in front of you now. Okay, so what we're going to do today is we're going to spend some time, we're going to go through a scenario together, we're going to answer several questions about that scenario, refresh our memories on some old vocabulary, some stuff from the first 6 weeks, our first semester that we may have forgotten. Okay, so please follow along. I'm going to have y'all do some discussions in your group, so I'll give you a few seconds in a lot of different places to kind of kick something around with your partner, and then we'll see if we can't get some answers from that. Okay, so follow along. On the Adventures of Cluck and Shelley worksheet, Cluck the chicken was at the top of poultry promontory nesting Shelley her egg. Shelley deciding to take off on an adventure, began to roll down the 45-foot slope of poultry promontory at a rate of 4 feet per second. 2 seconds later, Cluck discovered Shelley was missing and began running down the slope to catch Shelley at a rate of 5 feet per second. When will Cluck catch Shelley? Will she be able to catch Shelley before she cracks her noggin at the bottom of the hill? Now, before we get into the specifics of the problem here, one of the things I want to kind of discuss with you is, unfortunately, we developed somewhere along the line, we've developed a pretty bad habit on our test taking strategy. And that habit is this. When we see a question that's really short, okay, it doesn't take many words to ask the question, I mean, almost like a half a sentence type questions, our brain translates that as like it's an easy question, something easy to understand. That's a question we want to try to answer. But then if a question like this one were to show up on a test, a lot of people go, up, too many words. It's going to be too hard to understand. There's too much information. I'm going to skip that one, or I'm just going to guess at it, and I'm going to move on to the next question. Unfortunately, that thinking, for whatever reason we got into that, that is backwards. Okay, honestly, I don't worry much about problems like this one where it takes a gigantic paragraph to set the problem up. I really don't worry about those. And I don't worry about these because they give us lots of information. Okay, lots of information. They're providing you with a bunch of stuff that you no longer have to figure out. It's sitting on the paper. All we have to do is answer the question that they ask. On the other hand, when they ask one of those 4-word questions, those are the ones that I really worry about, because that tells me, hey, here is information that we expect you to know already. Go do it. Okay, those are the questions that I worry about for us. I'd very much not like to worry about these questions, because in a lot of cases, these are not that difficult. So I want us to kind of break free of that thinking of, oh, there's too many words, it must be a hard question. Some of the easiest questions I've ever seen on a tax or on a star are questions where it takes a big paragraph. They go through this big, long, elaborate explanation, and then they ask us something stupid. Okay, but if you've given up on the question and or guessed at it already because you already decided it was going to be too hard, you may have just missed out on a very, very easy question because we were, for lack of a better way of putting it, we were just too lazy to read it. Okay, so kind of let's start to reverse our thinking a little bit and try every question. You never know. I mean, the length of the question doesn't mean it's going to be easy or hard. It's just a question. Okay, think about every question the same way. Okay, so let's have a look here. Question number 1, what are the independent and dependent variables? Okay, now these terms, okay, in your groups, I want us to discuss what is independent and dependent. Those of you that have been here all year, we've talked about these two terms before. I want you to come up with a basic explanation for what does it mean when they say an independent variable, what does it mean when they say an independent variable. So with your group members, talk it out, remind each other, what does it mean independent and dependent? We'll get an answer here in just a second. Okay, what kind of explanations did we come up with? Who can tell us what does it mean when they say independent or dependent variables? Anybody have a shot at it? X and Y, absolutely. Independent and independent and dependent. One of them's X, one of them's Y. Okay, something more. What else? Well, we already got that they're variables. One of them's X, one of them's Y. I think you're onto a word, but I think you got it confused with a different one. Anything anybody else can offer for independent and dependent? Okay. Now, independent and dependent. Okay, we absolutely every single one of us are responsible for this. Okay, because it's very much fair game on the test. Independent variables. Okay, what I always say about independent variables is it's something that is beyond our control. Okay, something that's beyond our control. Okay, and when time is an issue in the problem, and those of you who've been here all year, you've heard me say this over and over before. When time is part of the problem, time is always an independent variable. And the example always goes like I can walk back there, I can grab that clock off the wall, I can smash it on the floor. Did I just stop time? No, I stopped the clock, but I didn't stop time. Okay, because it operates independent of any influence from us. Okay, when time is part of the problem, it is always independent and it's always going to get the x-axis. Okay, if time is in the problem, it's always going to get the x-axis. Whatever gets the y-axis is what we call the dependent variable. Okay, and the dependent variable, what it means is it depends. Okay, that's like if I were to ask you a question and say, how far have I run? What does that mean? I mean, how far have I run? Okay, you can't answer that question, can you? Why can't you answer that question? Okay, well, it doesn't make sense because it depends upon more information. We need to know where did I start at? Okay, if you're asking me how far have I run? Well, it may depend on where I started and then where I am, or it may depend on how much time has elapsed between the time I started running and the time that I'm currently running. Okay, so it depends upon more information. That is a dependent variable. It depends upon more information. Okay, so now in your groups, okay, now that we know what independent and dependent is, have a look at the problem. Okay, reread the Adventures of Cluck and Shelley here if you need to. Let's decide what information is going to be independent, what information is going to be dependent. Go. Okay, what did we come up with? What do you think is going to be the independent variable here? What kind of information is going to be on the x-axis? Okay. Now remember, okay, what I said in the break there is independent and dependent. We're talking about the axes, okay, the x-axis and the y-axis. Okay, what kind of information is getting on the x-axis? Okay. Time, absolutely. Okay, so that's one of the things we said. If time is part of the problem, time is going to get the independent variable, so that's going to be on the x-axis. So the answer to the first part of the question here on question number 1, okay, time is independent. Okay. Now, what kind of information is going to be dependent? Feet, exactly. Okay, and this is a common, typical type of um, problem. Okay, where time is measured as independent along the x-axis and some amount of distance is measured dependently on the x-axis. The amount of distance that's traveled is going to depend upon the independent variable, which is time. Okay, so good. There we go. All right, let's have a look at question number 2. Is the relation continuous or discrete? Here are a couple of vocabulary terms. Again, for those of you that have been here all year, this is something that we've talked about before, and we are responsible for the terms continuous and discrete. Okay, so search your memory banks. Let's see if we can't come up with that. Discuss it in your group. See if y'all can't find out what is the meaning of continuous and discrete. Okay, so what do these vocabulary terms mean? Continuous and discrete. Somebody got an explanation? Joe, what'd you say in the discussion? What's the what's with continuous and discrete? Okay, continuous keeps on going and discrete has stopping points or ends. Okay, and that's not a bad way of explaining either one of those, but it's not totally correct. So here's what you need to know. The word continuous in the English language means it doesn't stop. Okay, it just keeps on going. Okay, that's not exactly true in a graph. Okay, but what we're talking about when we say continuous in a graph is that there's no gaps in the information. Like it's okay if we draw a graph that goes from 0 seconds to 1 second to 2 seconds to 3 seconds, that's fine. Now, is there any information in between 1 second and 2 seconds? Well, there might be if we connect it with a line. But if we don't have like the actual numbers that are between there may be a little bit of a gap. So that's not what we mean when we say it doesn't have gaps. What we're talking about is like a graph. If the graph doesn't go from 0 second to 1 second to 2, and then skips over 3, 4, and 5, and then shows up again at 6 seconds, 7 seconds, 8 seconds. If it doesn't do that, if it doesn't like have a big break in the middle of it, then that's what we call continuous. Okay, discrete would be like maybe you have information at 0 seconds, and then at 2 seconds, and then 8 seconds, and then 20 seconds, and 22 seconds, where it's not very regimented. It doesn't happen consistently. There's breaks in the way that it's done. That is a discrete graph. Okay. Now, think about this problem. The question says, is the relation continuous or discrete? Okay. Well, the egg takes off going down this hill. Okay. A couple seconds later, the chicken takes off running after the egg. Now, does it say anything about the egg stopping at some point in time, or the chicken taking a rest break, or anything like that? Or does it basically roll and run until the completion of the problem? Okay. Are there any breaks in it, or does it continue kind of a start to finish type of a deal? Yeah, it's a start to finish type of a deal. That would be continuous. Okay. So question number 2, if I can get my page to respond. Question number 2 is continuous. Okay. If you've lost that vocabulary, if you didn't remember continuous and discrete, that is something that we need to know. They can ask that. Got the wrong page. Okay. Now, you've got charts. The page tells us to build tables to represent the distance traveled as a function of time for both Shelley and Cluck. The charts have been begun for you, but they are incomplete. So in your groups, take a minute, look and see what's happening with each chart, and fill in the rest of the missing information. Okay, now this should have been pretty much a no-brainer. Okay, you ought to be able to look at that chart, establish what's going on in the chart, and fill in the rest of the values. Okay, so what did you get on the left-hand chart there? What did it go? 0, 4, then what happens with the rest of the blanks? Counting upwards by 4s, yeah. Okay, so very easy there. Good job. Okay, now what about the other chart? Now, somebody pointed out during the break, we got a couple of question marks leading off the chart. We'll come back to that here in just a second. Okay, but let's start here with the at 2 seconds we get a 0, 3 seconds we get a 5. What happens after that? Yeah, yeah, counting by 5s. Okay, and obviously we could continue these charts for as long as the problem may need us to continue the charts. Okay, yeah, now we'll come back to these guys here in just a second because one of the questions is going to deal with what's going on right there. So we'll come back to that. Okay, now question number 4 asks, if both rates remain constant, what type of parent function can be used to represent Shelley and Cluck? Okay, well, here's a little bit more vocabulary. Parent function. This is another term that we are responsible for, and it's something that we've talked about in the first semester of Algebra 1. Okay, so in your groups, again, hopefully, let's find the definition or at least a plain English explanation for what is a parent function. All right, parent function. Okay, this is a term that everybody is responsible for. Okay, the basic explanation of a parent function is it is a function that has not been changed or altered in any way. Okay, it hasn't been moved upwards or downwards in the graph, hasn't been left or right in the graph, it hasn't been widened or compressed in any way, it hasn't been turned upside down. It is the most basic form of an equation. Okay, so let's think about this question. What type of parent function can be used to represent Shelley and Cluck? Okay, well, there's different types of functions out there. Okay, there's linear, there's quadratic, there's cubic, there's all kinds of stuff. Okay, well, what type of a graph do you think this is going to generate? Okay, based upon these points that you've got written down in your chart, what do you think? It's going to be a line. This is going to be a linear parent function. Exactly right. Okay, so question number 4. I'm out of space here on my board. Let's see if I can find some more. Okay, question number 4, linear. Okay, that is a linear function. It's not a linear parent function because it's got some particular values that are doing some different things to the graph, but it is a line. Its parent function would be a line. Okay. Question number 5, numerically, how would Cluck's distance be represented at times of 0 and 1 seconds? This is going back to those question marks. Okay. Think a bit, and you may need to reread the problem. Let's see if we can find an explanation for how come these two values at the top of Cluck's chart are question marks. Talk about it in your group for a second. Let's see if we can get an answer. Okay, did anybody come up with an explanation for what's going on with the question marks there? No? Yeah, that's it. Cluck. Okay, does Cluck get started? I mean, as soon as Shelley starts rolling down the hill, what does Cluck do? Nothing. It takes, as it says in the problem, it takes Cluck 2 seconds to notice that Shelley's rolling down the hill. So in essence, Shelley gets a 2-second head start on Cluck. Okay, well, now we need to kind of figure out, as question 5 says, how would Cluck's distance be represented at times of 0 and 1 seconds? Okay, so if we are trying to fill in this information here and here with numbers, okay, well, what kind of numbers is it going to need to be? Yeah, negative values. Okay, if this part of the graph from here going that direction is counting positively, then doesn't it stand to reason that counting from here this direction, it's going to have to count negatively. Okay, could we fill in those values with a -5 and a -10? Yeah, we could fill in the chart with that. Okay, can anybody think of anything that's kind of like fundamentally wrong with putting negative numbers right there? Okay, how about this? What kind of information is in this column? Distance, right? Okay, that is distance. So are we saying that Cluck has traveled -5 feet after 1 second? -10 feet at 0 seconds? That doesn't really make any sense, right? Okay, is there any such thing as negative distance? Okay, there's no such thing as negative distance. There's only distance. Okay, so what we have here is we have some numbers that suggest Cluck is traveling in a negative distance direction, which doesn't really make any sense. It kind of messes with our mind a little bit, but you have to understand that this is a situation that is being represented by a line, and that line is going to continue on even if it goes into values that our brain doesn't want to accept. Okay, so there are the values for question number 5. Yeah, that's going to happen sometimes. We're going to get some numbers in our equations that we kind of already know. That's impossible. Cluck is not run after 0 seconds. She hadn't traveled -10 feet. That doesn't make any sense. But we're going to have the equation because later on in the graph, when we get to the positive feet, that's going to become information that we need. Oops, that was the wrong button. All right, question number 6. What is the particular function for Shelley, assuming a constant rate? And 7, what is the particular function for Cluck, assuming a constant rate? Now, what these are asking for is these are asking for the equation. These graphs that these charts that you've just built, there's an equation that will give us these values. They're asking us to write the equations. So in your groups, let's see if we can't figure out what the y equals mx plus b for 6 is, and also what the y equals mx plus b for 7 is. Okay, ready, go. Okay, what kind of information did we come up with on the chart on the left? Okay, what do you think? Anybody got a good guess at it? 4x plus 1, like that. Okay, let's have a look. Okay, all right, the 4, does that explain how we are moving from one point in the chart to the other? Does it increase by 4 each time? Surely does. Okay, how about the starting point of the graph? Okay, well, the 1 doesn't represent an increase. The 1 represents where does the graph begin? Okay, does it begin at 1? It begins at 0, so the egg takes off at the origin. Okay, so that should be a 0 there. Okay, all right. How about the chicken? 5x plus 0. Okay, here's the answer. Okay, what do y'all think about 5x plus 0? Y'all agree with that? Okay. All right. So let's look at it one number at a time here. 5x. So we're saying it slopes 5. Is that how it moves from one point to the other? Goes up by 5? Yes, it does. Does the graph begin at 0? It doesn't. Yeah, it doesn't come through the origin. Okay, now this is kind of back to that same old problem we had just a minute ago. There is no such thing as negative distance, but this line is going to have to cross the y-axis somewhere so that these values can do what those values need to do. And that's going to happen at -10. Okay, so there are your two equations that go along with Shelley and Cluck. Okay, so there's 6 and 7. Yes, we did. Okay, we filled in the -10 and that -5 in the graph on -5, in the chart on question 5. Okay, now on 8, it says graph both of the functions on the same coordinate plane. Scale and label axes over an appropriate domain and range for the situation. Now we're running low on time, so I'm going to kind of start speeding you through some of this stuff. Now, it doesn't give you axes. It doesn't say here is the x-axis, here is the y-axis, so it leaves it completely up to us. Okay? Now, there's a lot of different ways to do this. Personally, I wouldn't leave a whole lot. I can't draw on this page. I wouldn't leave a whole lot of extra space in the graph for negative values. And the reason why I wouldn't leave a whole lot of space for negative values is because we're dealing with positive time, and for the most part, we're dealing with positive distance. Okay, so I wouldn't leave a whole lot of room for time. Okay, maybe 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and you can come up with your own graph. And what you're going to find is when you invent, places that you're going to put your axes and how big you're going to make the steps in each graph, sometimes you're going to guess really well and sometimes you're going to guess really badly. And it doesn't matter if you guess badly, then you will simply try to guess again. Okay, but graphing our equations from above, question 6 says 4x plus 0. Okay, on this top equation, on equation number 6, where am I going to have this equation cross the y-axis at? Okay, equation from question number 6, where's it cross the y-axis at? Okay, question number 6, where's it cross the y-axis at? 0. Okay, it's right there. Y equals mx plus b. It crosses at 0. Okay, where does it go from there? Up 4 over 1, up 4 over 1. Okay, so in my graph here, I'm going to do the best I can to go up 4 over 1. I drew a graph in a big hurry, so my points aren't going to be very good. Okay, but you can see basically the graph is going to do something like that. Okay, how about the graph from number 7? Where does it begin at? Starts at -10. Okay, so here we're down there in that negative distance thing, which we didn't really want. Yep, it goes up 5 over 1, exactly. Up 5 over 1, up 5 over 1. Okay, now I realize my graph is not to scale, and I should have labeled this. This is time. This is distance. Okay, my graph is not drawn to scale, but you can see that the graph is, okay, it's growing closer together. Okay, it's getting closer together. Let's see what our next question asks us. Okay. 9, compare and contrast the slopes and intercepts of the two functions in relation to the problem situation. Now what that means, guys, is there is something in plain English that can be said about how these graphs begin, how they move as they go through the graph. Okay, so what the question is asking now is it's wanting us to come up with a plain English explanation describing what's the slope doing in this problem? Or the slopes, what are they doing? And the y-intercepts, what are they doing? Okay, so spend some time, just a second, in your graph. Let's see if you can't come up with a plain English explanation for what the slopes are doing to these graphs and what the y-intercepts have done to these graphs. Okay, now a basic explanation for what's happening here. Okay, did anybody come up with anything to describe what the slopes are doing? Yeah, obviously they're both increasing. Okay, they're both going upwards. Okay, stuff like that. But can you say, I mean, putting it into context, okay, this situation about what's happening to this problem. Okay, the egg is rolling, the chicken is running. Are they rolling and running at the same speed? Okay, obviously not. Okay, so we've got the chicken is running faster than the egg, so they're getting closer together. Okay, so could an explanation be that one is moving faster than the other, that they're about to catch up to each other, something like that? Sure, that's kind of an explanation of what's happening with slope. Now, what about an explanation on the y-intercepts? They're obviously not at the same place, so a basic explanation could be something like one got a head start on the other. The egg had a 10-foot head start on the chicken before the chicken started running, stuff like that. Okay. Now the rest of the questions that are on there ask you specific things. Okay, about how far away things are, how much time has gone by. Well, folks, that's what the equations are for. Okay, y is distance, just like it is in the graph. So if they give you a distance, we can plug it in to either location for y to figure out what's going on with x, and x is the amount of time. Okay, x is the amount of time. They can give us a certain amount of time, which we can plug in for x and figure out what's going on with y. Once we really get to this point of the problem, we can answer anything. They can say, what happens after 4 days and 16 hours? And we can find out how far the chicken and the egg have moved and run if it continues on that far. Okay, so that's all we're going to do with this. We were just kind of trying to get our feet wet. You don't have to turn this page in or anything like that. I just wanted to introduce you to the type of problems that you're going to be seeing as we go through this unit.